bonus. Anyone else have the bonus for today? It's now or never on the bonus. Okay, a couple of things. I'm handing back the signed syllabus thing because I've made a change in our grades. I've added a quiz category because it wasn't in there. So I have a new one of these to hand to you. You need to sign it so that you know the deal. And I've highlighted on here, you can kind of see it in brown and like gray, what's changed. I've taken quizzes and added it in there. The quizzes category is added. It's now 5% of the class, which took your final exam grade and brought it down 5%. So a little less weight on the final, but it gives me an opportunity to give quizzes, all right? So if you could, please sign and return that. I thought this was interesting because it says, I blank have read the syllabus and watched the orientation video. Well, my YouTube analytics allow me to see who's watched it, like how many people have watched it and how long it was watched for. I only had 6 views of that video. So I found it kind of disturbing that there's 23 students in here that all signed this paper saying they watched the video, but I only had 6 views. I'm not quite sure what that means. It's just views worldwide. It doesn't matter. Yeah. So, maybe YouTube's messed up. Okay. The next order of business. Yeah, I'll take those. Well, let's let everyone sign them. Let's just give those to me in a minute. I want everyone to have an opportunity to sign those. The next order of business is, I told you I was going to print out the copies until they told me to stop or something. No, not yet. So I have first the notes from 10.4, and they're actually the right way now. But it required me doing it by hand. So there's 10.4. Take a copy, pass it around, please. Let's get that moving because I've got 10.5 and 10.6 coming next. Huh? Oh, we're not going that far, but I want to get these off my desk. Y'all take them and go around. All right. I've collected the bonus, so this is your only opportunity to turn in the bonus right now. I've also handed out I made changes to the syllabus, so please sign in and return that thing. I'll take the signed copies now. Bonus. No, not this one. I want the other one. Here we go. I have another copy. I've added a quiz category. It's only 5 points, but you can see it there. It took 5 off the final. Do y'all see that? I've changed this. I need this signed and given back to me. I added a quiz category, reduced the value of the final by 5%, and put 5% on a quiz category. Not that one. I need this one signed. That one. Oh, sorry. Yeah. Okay. Thank you. Anybody else? 10.6 notes. Okay. Thank you. 10.5. Thank you. Okay, does anybody still need to sign the syllabus thing? Give it to me. Extra one. Okay. The signed one? Yeah, I need that one, the new one. The old one you can keep, because it's not official anymore. Thank you. There you go. Anybody else? All right. Trying to get done with all this. Attendance. I feel like a administrator up here today. All right, we have lots to do, so let's get started. We left off last time. We didn't quite get through 10.3. I was able to finish the homework that I gave you. I was able to finish it before class today. And it was a lot of the front end of the assignment was tedious, and just a lot of dot products and things like that. But towards the end, the problems required a little more thinking. So just remember that the expectation, again, is that you would have that done. Starting next week, that quiz category could come in the form of me just saying, let me see your homework. You don't have it? 0. Okay? You don't have it? 0. Okay, that's why I added the quiz category. You've got to keep up with your homework in here. And I understand, I was talking to some students about this, between Monday and Wednesday, you may not be able to do it all. I expect you to, but I understand if you can't, if you come up a little short on it. But between Wednesday, Monday class, I expect it to be done. All right, let's get working here. If you have any questions on homework, I just posted the solutions, so it could be anything. Yeah, the quiz category now can be anything that I want to really call a quiz. It could be attendance. It could be anything, really. Yes. I won't ever really pick it up because I'm providing the answers to you, so there's no need for me to see. I mean, homework, hopefully, you know, I mean, you've got to do it. But like there's a problem in the homework, right? That you had to take the dot product to 2 vectors and find a value x that would make them, I forget what it was, something like, it was like make it where it was a normal vector, something like that. It required doing a quadratic equation, solving quadratic, using quadratic formula. You know, if I start talking about that right now during class, like, okay, this is like the homework problem that you did where you had to use a quadratic formula. If you're just sitting there going, you know, I have no idea what he's talking about. That hurts you, I think. I mean, because I expect you to have run into that already. All right, here we go. I need to start. We're already almost 10 minutes in. Okay, we stopped at this whole idea of, I guess neither one of those really helps. The idea of the unit vector, I think, is where we were before this. Oh no, we had done dot products orthogonal or not, parallel. Okay, we stopped there. We had a triangle, 3 points, and we had to determine whether or not it was a right triangle. There was one just like that in the homework. Okay, so now we talk about vector projections. So you have the notes in front of you. Basically it says if we have any 2 vectors, non-zero vectors, we can project one of them onto the other. And I have a visual aid here. So right now I have a blue vector, right? And I have a red vector. And I can move these around. And what you can kind of see on here, do y'all see that? It's purple vector right there. That purple vector is the projection of the red vector onto the blue one. And to help you see it, it's almost like what we call dropping a perpendicular from that red down to the blue one, and that creates a new vector. Do y'all see it? Now, what if I grab the tip of this red one and move it out, let's say over here, right about here, the red one? What's going to happen to that purple one? It's just getting longer, right? Still pointing in the same direction, still parallel to the blue one, it's just longer. What happens if I make that red vector come over here? Where's the purple one going to be? Will there be a purple one? So let's see. Here I still have the purple one. It's getting shorter and shorter. It'll be pointed out the other direction. So even though the blue vector doesn't exist over here, well, remember, vectors, you can slide them around. So I am projecting this red one onto the blue one, but since the blue one's not there, I'm projecting onto this like imaginary line that extends through. And so this purple vector, is it parallel to the blue one? It's parallel, right? It just points in the opposite direction of the blue one. Y'all see that? Okay, so projections of vectors onto vectors become new vectors. Now, what if I switch this up? What if I do, let me move that blue one over here. Let's change quadrants. What if I, instead of doing the red onto the blue, which you can hopefully see here again, there's the red onto the blue. What if I say project the blue onto the red instead? Now the shadow or projection down would look like this. I have to change this drop-down menu. Now you see the purple one is on the red, and the construction of this is that a right triangle. So a perpendicular drop down to where it hits the red. Totally different things, right? There's the projection of the blue onto red. Here's the projection of the red onto blue. So you can ask either one. Now, do they come up with the same answers? No, they're totally different vectors, aren't they? So it matters. If I say project blue onto red or red onto blue, totally different results. What if I do the blue onto red, and I pull my blue tip over here, backwards here, to this point over here? Where's that purple one going to be? Pointing the opposite direction of red, right? But it'll be parallel to red. See that? So those are called vector projections. Now, why is that useful? Yes. Can the blue? Yes. Whoa. That's not what I meant to do. Let me make the red one smaller. How about that? There it's, I don't know if you can tell, the red one stops here. Do you see that? And then the blue one is further out. So its projection is along, again, imaginary line that goes out extended past the red one. So that projection of the blue onto red there would actually be a vector that's longer than the red one was, right? So we're going to be concerned with two things here. I'm going to give you two vectors. I'm going to want us to be able to actually find this vector. What is it? Okay, what is that vector? And then, what's its length? And those two things are called two different things. One of them is called the scalar projection. The other one is called the vector projection. And that's what the next set of notes is about. So that's me pretty much saying, that's me talking about, it's one, project on the next. But here's the notation. If we want to take a vector, u, and project it onto v, u onto v, here's the notation. So the u is here and the v is a subscript. The way I like to look at that is, isn't the u like above the v here in this notation? So that u is projected onto the v. So this would be like blue is projected onto red. That's the notation for it. And here's the formula for it. So if you want to know the projection of u onto v, you have to dot the two vectors together, divide by the length of v squared, that's the length of v squared, and then times v. So someone tell me, I never brought up my other program. Let me see if I can do it without killing my computer. Where'd it go? Sorry. I lost my notes there. All right. So someone please help me. Tell me what this quantity will become right here. What will that quantity be? Just a number, right? That's a scalar. Because the dot product is a number, isn't it? The denominator is a vector's magnitude squared, so it's a number squared. So that's all a number, isn't it? And then the v out here is a vector. What's a scalar times a vector? Well, it's a vector. And it happens to be a multiple of v, which means it should be parallel to v. So that's basically saying that that purple vector, remember, lived on the same vector that we were projecting onto. That just confirms that that formula will give us a scalar multiple of v. That's what I say right there. All right. Did I miss anything on the bottom of those notes? I don't think I did. Here's the next one. So that projection of u onto v, that gives you a vector, doesn't it? I said we're going to want to know that purple as a vector. This one gives you the length of that vector, and it's called the component of u onto v, also known as, and I didn't put it in my notes. Oh, no, I did. There it is. It's called the scalar projection. Scalar projection. In other words, the length of that projection. Scalar meaning number for the length of that projection. And the notation we use is component of u onto v. And the formula is just the dot product of the two vectors over the length of the v. Not the length of the v squared like in the previous formula, just the length. So those are two formulas that we'll need, and we can proceed. Projection is a vector, scalar is a number. Yes? Okay, 1039. The component of u onto v. Or if you want to say the whole word component, you can also say comp u onto v, but you have to know what comp means. Comp is component. All right. Well, so I'm going back to this this drawing I have here. This program that I have written here, this actually just does the computation. So now instead of just having vectors out here, here's the projection vector. Let's see if that makes sense, that projection vector. Does it look like that I go out to the left 2.6 and down 1.2 for that purple one? And its length is about 2.8. So nothing new here, just added that for you. I guess to also point out that there are two distinct things, a vector versus a number. Now, unfortunately, I couldn't get Mathematica to throw the angled bracket around there, so I had to use the braces. So, but it is a vector, sorry. Just easier for me to do. Anybody here interested in coding in Mathematica? If you are, I can share with you all the code that I wrote for this. I don't mind sharing it with you. We only had one computer science major, didn't we? Last time we asked, right? Or I asked you last time, right? So this isn't very interesting. That's the code. That's the code that I wrote to make that happen, right here. All right. Next is an example. So given two vectors, u and v, we want to do this computation. So let's do this computation real quick. First, let's do the projection of u onto v. Now, by definition, it's in your notes, it's v dot u, right, over magnitude of v squared times the vector v. Now, you can't mix those letters up. I mean, everything's got to be right, okay? You can't have u's in your denominator. So let's do this. I'm going to need to find the dot product and the length. So let me do that kind of as scratch work. What's v dot u? Well, if you did your homework, you probably are bored of this by now. Negative 6, 28 is 22. The magnitude of v is the square root of 9 plus 49, correct? Which is the square root of 58. So now I'm going to come back up here, and I'm going to write down what I've got. The number in front of v is what? My dot product, 22 over, oh, did I square? I forgot to square. Let me write that underneath here. I could square it on the next step, but it'll be 58, right, when I square it. So it'll be 22 over 58, and then times v, but the vector v is negative 3, 7. And I can reduce 22 over 58 to be what? 11 over 29. And then I will distribute or pass the scalar through the vector to give me negative 33 over 29, and then 77 over 29. So that is the vector projection of u onto v. That vector should be parallel to what? To which vector, u or v? It should be parallel to v, right? And as far as the length of it, that would be the other computation, right? Comp u onto v. That's its length. Now, you can cheat, and you can get the length right away right now by just taking the magnitude of that, right? You could. But I'm going to use a formula just so you can see it being used once. Out of room. Are y'all okay with me just like clearing this out and starting, just staying on this page? Yes, I did. That's what I'm saying. But I'm going to write the formula down, just plug things in, that's all. I just wanted you to see it one time, and that way we can say it was somewhat thorough. So I have the component of u onto v is equal to, it's still v dot u, but now it's just magnitude of v. And we did the dot was 22, and the magnitude was root 58, wasn't it? And that would be it. And we could get a decimal number, approximation of it, but I'll just leave it like that. All right, questions? Pretty straightforward. We're all right with this? Now I ask you to sketch it here, which means you could draw it. It's two-dimensional. You could draw the vectors. I'm not going to draw them, but you could just to see that they are parallel to each other. Moving along. Now it doesn't look like I changed anything, but I did, right? What did I do here? I want to go v onto u instead now, so things will change. If I say, let's find projection of v onto u, then my formula changes. It's u dot v over magnitude of u squared times u. Now, u dot v, won't that be the same as v dot u? I mean, I use the same numbers, right? These are the same two vectors from previous example. So remember, dot products are commutative. So that top dot product is still 22. The only difference is I need the length of u instead of the length of v. The length of u is the square root of 4 plus 16, which is square root of 20. But then I want to square it in the formula, right? So we'll get, I'm going back up here, it was 22 for the dot product over the magnitude squared, which gives us 20, and then times the u vector 2, 4. And you can reduce things, what's that, 11 tenths? And then multiply 11 tenths through, you get 22 tenths, or it's hard for me to erase with this new little thing I have. It requires me going up here and grabbing the eraser. So to me, that's kind of one extra step that I don't like. What would this be, though, if I multiplied the 22 through or scaled that, reduced the fraction? What do we get? 11 fifths. And the next one, 22 fifths. Good. All right. So that is our projection of V onto U. And then you find its length. Do you think you get the length yourself? Yeah. So just be careful. That's all. Just you got to get the order of those things right. Was there a question? Good. Now, if we move this thing, we're not ready for this. Is a 3D one. Okay, yeah, this will work. Clearing out. All right, I'm going to try and clarify this problem here that kind of caused some trouble in class. What we're trying to do is show that we can find a V, that the component of U on V is equal to 3. So I'm going to start by defining a vector V to be V1, V2, V3. I don't know what those are, but I need it to satisfy this, which means that I need V dot U over the magnitude of V to be equal to 3. So first things first, what is V dot U? Now, when we dot the 2, we get 4V1 minus V3. Now, what is the magnitude of V? It is the square root of V1 squared plus V2 squared plus V3 squared. Okay, so we need, when we say over here on the right side that we need this to be true, then that's the same as saying V dot U needs to be equal to 3 magnitude of V. Now in class what I did is I said, okay, let's let the magnitude of V be 1. That causes some problems though, because once we fix it to be 1, there's certain restrictions on what the components can be. So I'm going to let it be a little more flexible here. The way I show it now is trying to avoid this in class, but I think it'll make more sense. Let's go ahead and just write out what this is, replacing our dot here and our magnitude in this equation with those two expressions. So we have 4V1 minus V3 is equal to 3 times the square root of V1 squared plus V2 squared plus V3 squared. Now we need to work through this. This is a pretty ugly looking thing here, but I'm going to try it. I'm going to square both sides of the equation. When I square the left side, that means I have to actually take the quantity and square it. So I get 16V1 squared minus 8V1V3 plus V3 squared. And when I square the right, I get a 9, and then everything under the root, it basically appears without the root anymore. So we get this. Okay, now this is a very ugly looking equation. I'm trying to figure out what V1, V2, and V3 are to make this true. So let's notice a couple things. Remember back in the dot product, when we did our V2s, no matter what V2 is, it's dead. It's going to get killed off. So I'm going to choose to let my V2 be equal to 0. So we did this in class, same thing. Let V2 equal 0. When I do that, all it does is kills off that one right there. But we still have an equation with 2 variables in it. So what I need to do now is let my V3 or my V1 be something. I'm going to choose to let my V3 be equal to, I'm just going to pick a number now. The number I'm going to pick, I could let it be 1 or 2 or 3. I can't let it be 0. Check it for yourself. If you let it be 0, then your solution for V1 becomes 0, and then they're all 0, and then it doesn't make sense. So I'm going to pick something. Now, I'm going to actually pick a multiple of basically something that's going to give me a multiple of 4, because I'm noticing that this is kind of like a quadratic equation here, and I want to be able to factor something out, so maybe it'll help. Let's see. I'm going to pick V3 to be 2. So let's see how this works out. I have 16V1 squared minus, let's see, 8. I have my 8 here, but then I'm going to multiply times V3, which is 2. So I get minus 16V1, then plus my V3 squared, which is going to be 4. And that equals 9 times my V1 squared plus, again, my V3 squared is 4. So I have 16V1 squared minus 16V1 plus 4 equals 9V1 squared plus 36. Now what I'd like to do is just move everything to one side. So I subtract a 9V1 squared. I get 7V1 squared. Let's see, I have minus 16V1. And then, let's see, I have negative 32. When I subtract 36 from both sides, equals 0. Now, those are some ugly numbers. But now I'd use a quadratic formula, okay, and I would get solutions. V equals, and I'm actually going to go ahead and get on Wolfram Alpha real quick, because my calculator doesn't have batteries. And I'm going to get a decimal solution. Okay. I'm done. As expected, I get 2 solutions. I get negative 1.2815, and then the other solution is 3.5672. I'm just going to avoid doing the exact answer, because all the radicals and stuff gets kind of ugly. So that's what V1 is supposed to be. I'm going to just choose one of these, and I think I'll just go with the positive one just for the heck of it. And let me see if I can get my vector V to work out now. So the V, remember, was V1, V2, V3. We said that V1 was going to be 3.5672. V2 we said was 0, and V3 we picked to be 2. So that's coming 0 and 2 comes from right there. And then, of course, what we just got as our answer is here. So let's check some things. What is U dot V over magnitude of V? All right, U dot V. So I have to take my U and dot it with my V. Remember, U dot V was right here. It's 4 times whatever I just got, 3.5672 minus V3, which we said was 2. So again, real quick, I'll be back. Okay, I've got 12.2688. So that, I'm going to come back down here and put it on the bottom here. I get 12.2688 divided by the magnitude of V. So magnitude of V, I'll do that down here. The magnitude of V, remember, is the square root of all the components squared. So 3.5672 squared plus 0 squared plus 2 squared is 4. And again, I go get it. All right. Now I've got, let me get this out of here. I get 4.08961 or something like that. And that's going to be on the bottom, 4.08961. Now if I divide those, and I'll keep you standing by here while I do this, 12.2688 divided by that, I get 2.99999, so approximately 3. And remember, that's what we wanted, right? We wanted way up here, there, for that to be true. And we just actually showed that that's true. So this vector v is a choice. It's not the only one. There's actually an infinite number of them, but that is a choice that would satisfy that the component of u onto v is equal to 3. So apologize about the confusion in class. I was trying to avoid having to do all of this, but looks like that's what we got to do. Okay, hope that helps. That's it. All right, we're going to move on. 10.4. These are the notes that are actually those. That is the homework assignment, right? That I gave you the other day. I sent to you email. Yeah, the back of the notes, but that's it right there. So I'm going to be working off 10.4. Anybody need 10.4? Everyone's got 10.4. It's all stapled correctly. I don't want to offer that last problem we just did as a bonus because it's really not bonus worthy. But it's definitely something that you should go and think about more. Yes. It would have been harder to do magnitude as 2. I mean, we could have, but it would have just been a little more work. That's right. All right, so opening up 10.4 here real quick. All right, we have cross product now. So far we have vectors, we can scale them, right? Scale them with a number that was like distribution through. Then we define the dot product, take two vectors, dot them, you get a number, right? Now is the second type of multiplication. So there's two types of vector multiplication. There's dot product, cross product. We don't have that in the numbers, right? Multiplication is just multiplication. There's no other type of multiplication. Here we have the cross product. So first let me start out by having you remember how we write vectors. If you have a vector in 3-dimensional or 2-dimensional here, if you write u as u1, u2, u3, then that's the same as u1 I j or u plus u2 j plus u3 k, right? So that was the different form using those standard basis vectors. Yes. You can do IJK on test. I prefer the angle brackets, so every time I see IJK, I go to brackets. It's really your call. And in fact, later on, maybe if you do a lot more math, you may completely step away from writing vectors with angle brackets. You might write a vector like this instead. You might do like a vertical vector instead. It just depends on how much more you're going to do. So go with your preference at this point. All right, so far we've defined dot product. We know it's a number. This new one, this new cross product, there's an important note about the cross product, and that it's only defined in 3-dimensional space. We don't have, so if you've got two vectors in 2D, and I say find the cross product, then you'll tell me that you can't, right? It's only in 3D. And that's the way it's defined. And it also makes more sense geometrically in 3D than it would in 2D. Okay. So here's the formula for the cross product. If I give you a vector u and a vector v, the cross product of u and v is denoted by u with this like an x. It's like the old school multiplication symbol. It's back. But now it means cross product, right? With v. And it can be computed using this formula. Now the formula, if you want to memorize it, you can. It's fine, no problems. Go ahead. Or if you don't want to memorize it, then we have a way of doing it by hand, which I'll show you. Now I wrote them, these two, the differences between these two, that one's using the IJK, this one's using just the angled brackets. But the same computations occur in both of them. Not many people that I know just memorize that formula. A lot of them just memorize how to do it. So there's really, like, I've seen two major ways of doing cross products by hand, of doing the computation. I'm kind of on the fence on which one I like more. One of them requires determinants, knowing what a determinant of a 2x2 matrix is. The other one requires nothing. So I usually show the one that requires nothing so that I don't have to go and talk about determinants. So what I'll instruct you is the way without determinants. If you want to find cross products using determinants, then I will refer you to YouTube. Just look it up, cross products, computations, whatever, and watch a video on it. It's pretty clean, all right? Here's the way I'm going to do it. I make a table. That's kind of what my table is going to look like when I do it, and then I do this multiplication and stuff. You'll see. You'll be expected, though, this is a big thing, you will be expected in this class to be able to do cross products on a calculator. So like on your midterm, when you get to cross products in problems, you don't want to be doing them by hand. So let's see, does everyone here have a graphing calculator or something? Graphing calculator? Yes? Is anybody not using a TI? So everyone has a TI? No, what do you have? Casio? You don't have one? Anyone? Doesn't have to be graphing necessarily, but so only one person doesn't have one and one person has a Casio. I'm pretty sure the Casio will do a cross product. Now the TIs, anybody working with anything like an 83 or an 84, TI 83, 84? I don't know. We'll have to see. If they can't do them, you can write a program to have it do it. And I'll be happy to sit down in my office and write the program into the calculator for you, where all you have to do is input the vectors and it'll spit out the cross product. Okay, but everyone on a test wants to have something do it for them as opposed to doing what I'm about to show you here. Because this is time consuming and tedious. No, the cross product is a vector. Yep. Yeah, see, notice in these formulas, the cross product comes out to be a vector. And we're going to talk about what it is in a second. But first, let's just do one by hand and see how nice it is. Okay, so the way that you do a cross product, first of all, you have to have two vectors in R3, which I have. And now I'm going to write a table. I'm going to do I hat, J hat, K hat, I hat, J hat, K hat. Okay. Now, if you've already done cross products in your life by hand, and you like it and you're happy, don't get all upset with me going, "Why are you doing this way, man? This way sucks. My way's better." That's fine. Okay, do it your way. But this is just for people who've never done it, a way to do it. Now, what you're going to do is you're going to write across the top. Let me go back to this blank formula if I can. Let me see, where was it? See what it says in this formula? Well, I'm covering it. But what are you supposed to write across the first row of that? After you do IJK, IJK, U1, U2, U3, U1, U2, U3, right? So it's your first vector, the numbers, twice. And then below it, the other vector's numbers twice. Y'all see it? Okay. That's what I'm about to do. Maybe. This thing is really weird. Okay, so my first vector is U. I'm going to do 2, -3, 5, and then repeat 2, -3, 5. The other one is 4, -1, 3, 4, -1, 3. All right. You ready? Start off when you do this guess I'll change my color. We're going to start with the I here, top left, and I'm going to multiply diagonally down and put my answer here. Okay? So what would that be? I times -3 times 3. Negative 9i, right? Negative 9i. Then I do the next we're going to move across the top. We're going to do I, now we're going to do j. Okay, so what's j going to be? Diagonally. So j 5, 4 is what? 20j. And then move on to the next one, which would be your k. So I'm going to go k, 2, 1. So that multiplies to be -2k. All right. Now what we're going to do, since we're at I and we can't go diagonally anymore, right? Because we're going to, won't we run out of, like, my table's not there anymore? What we're going to do is that I, we're going to go diagonally the other direction so that we can get this box. So you go diagonally up from there. Okay, so let's do it. We would have I 5 and -1, which would be -5i. The next one would be j 2 and 3, which would be 6j. And then k 3 and -3 and 4, which would be -12k. Is that all right? Is this, you don't like this way or what? Calculator is much easier, right? Okay, does anyone have their calculator? Has anyone tried this yet? No, on their calculator? Okay, well, let's save that. Let's save it. We still got to finish this. We're not done. The question is, how do we interpret these answers? Because the answer is in here, just how do we get it? Combine like terms, but there's a trick to this. There's something else we have to do. That's right. We want to look at this as having like two sets of answers. The set that we got when we went diagonally down left to right, and then the other set was when we went down diagonally right to left, right? Now I'm going to write something over here to help you understand what needs to be done. This was U1, U2, U3, U1, U2, U3, V1, V2, V3, V1, V2, V3. Okay, let's look just at the I's, just at the I's. I go I down here, here, here. That goes in here. That was U2, V3I. Do you agree? The I's the other way, went diagonally the other way, came out to be what? U3, V2I? Yes? Now, look in your notes on the formula, 10.4.3. Look at the formula for 10.4.3, and what do you have on the row that has the IJK? What do you have in front of the I? U2, V3 minus U3, V2. What we have is U2, V3. We need to change that from being positive to what? Negative in order for it to match the formula. So in other words, before we can put these two together, we have to change everything over here, change the sign, or subtract everything here. So here's what I'll do. I'm going to write the ones on the right first. -9i, but now I'm going to subtract everything I see over here. I'm going to subtract. So subtract -5i, and you get what? +5i? So see what I'm doing or not? Okay. Now the j's. 20j, subtract 6j. And then negative 2k, subtract negative 12k, which becomes 12k. I feel like I lost you. Are y'all all right with that or not? Negative 4i plus 14j plus 10k, which is the same as the vector negative 4, 14, 10. That's it right there. You can. If you're like real good at memorization, that's fine. I think so. Yeah. Now that's supposed to be our answer, right? So what happened was we took two vectors, right? We crossed them, and what came out? A vector, right? The big question now is, what does this vector represent? So I want to show you something. If we got this right, this should happen. Let's see. I want you to dot this with u. What do you get when you dot that with u? What's the first multiplication? You get negative 8 minus 42 plus 50 is 0, which means this vector is what? Orthogonal or perpendicular to u, isn't it? Dot it with v. Negative 16, negative 14, and 30. Add them up, 0. So it's orthogonal to the other one, which means it's orthogonal to both. The cross product of two vectors creates a vector which is perpendicular to both vectors. This is a huge deal. I think I say that here in my notes. I'm sorry? We shouldn't have cross product things yet. Yeah, that's probably the thing. Yeah. Okay, this is the major result here. So we already know the cross product yields a new vector. What makes this new vector so special is that it's always perpendicular or orthogonal to both the vectors it came from. We often use cross products when we are trying to find a vector that's perpendicular to two other vectors. So show that the cross product is orthogonal to this. So this is the problem we just did, isn't it? So we already computed what this cross product was. That cross product was negative 4, 14, and 10, or negative 10? 10. And we just said if I want to show that that's orthogonal to both, I just have to dot them. And we did that mentally. Are we happy with that? Dotting both, we got 0. So it is. Good news. So dot that with u, you should get 0. Take it, dot it with v, you should get 0, which would make it orthogonal to both. So here's the cross product in three-dimensional space. Now this can get a little bit hard to see. And in fact, I'm going to have to close this, I believe, in order to do this properly. Man, it's really strange how this program affects my computer. I'm not happy with it. I'm in one of those frozen states here. Frickin' technology. Okay, well, let's talk about what this is with markers, which is what I was going to do anyway. If I have two vectors sitting in three-dimensional space like this, right? Two vectors sitting there. Since they're vectors, I can slide them around anywhere I want. I can put them tail to tail like this. Now, if I take the cross product of these two vectors, I should create a third vector, which is orthogonal to both. Orthogonal means it should be perpendicular to both, right? So where is that vector here? Well, it's some vector, it's orthogonal to both. That means it would have to be orthogonal to this one, right? 90 degrees to this one. But there's an infinite number of vectors 90 degrees. These are all 90 degrees, aren't they? All of those are 90 degrees to this vector right here. Now, over here, I have an infinite number of vectors that are orthogonal to both here. The vector that we find with the cross product has to be orthogonal to both at the same time, which is this one right here. So no matter how you look at it, it's orthogonal to that marker. It's orthogonal to those two. Got it? See it? Now, when you do a cross product and you have a vector, let's say this is the vector u, and the green one here is v. When you take the cross product of these two vectors, you get a vector that pops out of both. The direction it pops out follows the right-hand rule. So if we take the cross product of u vector, is my fingers, and I curl into v or cross into v, then my cross product will come out in the direction of my thumb. That's the way cross products work. So again, if that's u and that's v, cross product would come out towards u. If I said now, instead of cross product u and v, I say cross product v and u, then I have to come over on the other side of this and curl my hand v to u, and now the cross product comes out this way, away from y'all. Okay? I'm pretty sure that my computer is no longer responding. Let's try Control-Alt-Delete. Okay, well at least, no. What I'm trying to get out of is the full screen mode of this. Okay, I'm out of full screen. I think I'm back. Well, this picture here, I think what I'll do is I'll pause. That's what it is. I can't record and do this. That's weird. That's never happened before. Well, so show now that u cross u is 0 for any vector. You cross a vector with itself, you have to get 0. So how could we show this? Yeah, exactly. Now we're going to do it in general, and I'm going to do it real quick. I'm not going to go through this too intense here. I would do ijk, ijk, and then I would do u1, u2, u3, u1, u2, u3. Then the other vectors itself, u1, u2, u3, u1, u2, u3. And then when I do diagonals, I do all my i's first. I get u2, u3, I. Now do the i's the other way, just to show it's going to cancel. Here, 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 I get u3, u2, I. But then what am I supposed to do with the i's in this one and this one? Subtract. So I subtract. I take the one on the right here. I subtract the one on the left. They're gone, aren't they? And that will happen for each one that you do. So it'll become what? Be careful. The 0 vector. On my notes, it's hard to see that that 0 is supposed to be a bolded 0. When you cross two vectors, you should get a vector. And so the vector that comes out of this is the vector 0, 0, 0. not the numerical value 0, 0, 0. In fact, I should probably change that in my notes to be more clear with it. Right? So please make that note, that change in your notes, okay? That's the 0 vector. All right, find a vector perpendicular to the plane that passes through the points blah, blah, blah. So what we have, we're starting to really now get to doing some problems that are going to be important for us. God, what's going on with this damn thing? This is where things start to really, we start to be able to create some really good problems on tests. When we start to talk about planes and trying to find things that are orthogonal to them. So this is a nice basic problem to get us pointed in that direction. So let's go ahead and do this one. All right, I'm going to catch up in the notes here. Find a plane that's orthogonal to both. I'm going to go back to Old Faithful here. I have 3 points, don't I? I have 3 points in space. And 1, 4, 6, I'll just label that one. -2, 5, -1, label that one. 1, -1, 1, label that. And now, what I'd like to do is imagine that those 3 points that create a triangle, right? It might not be a right triangle, but it's a triangle nonetheless, right? We just have some triangles sitting out there in space connected by 3 points. So here's some arbitrary triangles sitting in 3-dimensional space, right? And those 3 points define a plane. This sheet of paper is a plane. It extends in every direction forever, right? But I'm just talking about this triangle, but that triangle itself is like a little plane, a piece of a plane. I want to find a vector that's orthogonal, perpendicular to this plane. Any vector that's perpendicular to this plane, right? Like this. So how can you find it? Okay, so just take any 2 points, connect them together with, let's say, V, and then the other 2, or another vector that goes from here to here, call that U, right? And if I cross those 2 vectors together, I should get a vector that comes out perpendicular to both. So that would give me a vector perpendicular to the plane. Do you all agree with that? I'm sorry, did I say parallel? What? I did? Okay. Well, I meant perpendicular. If I cross the 2, I'll get a vector that is perpendicular to the. Just find a vector perpendicular to the plane that passed. Okay. All right, so V vector is the vector 0, 5, 5, right? The U vector, I'm just subtracting coordinates, right? 2, so -3, 6, -2. Now I have to cross them. Now I truly don't want to do it by hand. My calculator's batteries died, so I need someone else's calculator that can do it. So has anyone looked yet? Let me see, what do you have there? 84 plus? Let's see. 89 will do it. Math menu, matrix menu, and do you have a... Oh, I didn't bring it because my batteries are dead. Thanks, though. I don't see it, but that doesn't mean it's not there. Where's that 89? Let me see the 89 real quick. It's called cross. There it is. Vector on. Okay, I'm just going to do this real quick. 0, 5, 5. Cross it with, is this new? This calculator? All the keys are real nice and nice, very responsive. Okay. -40, -15, +15. -40. What did I say? -40, -15, +15. Probably could have done it by hand by now. This was V cross U. Yes, it is different. It points the other direction. It's the same vector, just pointing the other direction, so just change the signs. So it'd be 40, 15, -15. That's it. That's the answer. That is a vector that is perpendicular to the plane. That's right. If you did 40, 15, -15. If you scaled it, it would still be perpendicular. Divide it all by 5. That would still be perpendicular. Divide it all by pi. Still perpendicular. Any scalar multiple of that except 0. You can't multiply by 0. So that is an example of a vector that is perpendicular to that plane. Got it? So that's going to be real important as we move on for you to be okay with that sort of computation. All right, next note here. If you recall, before we had something with dot product that said u dot v was equal to the magnitude of u times the magnitude of v times cosine of the angle between them. This is the similar type thing with cross products, except that it's not just u cross v, it's the magnitude of u cross v. So when you cross two vectors, you get this vector that pops out, right? Perpendicular, pops out of there. The length of that vector is the length of u times the length of v times sine of the angle between the two vectors instead of cosine. So here's an example. If v is 7, u is 3, angle between them's at, find that cross. So you've got this in your notes, so I'm going to switch over, write it down. I have the magnitude of u cross v should be equal to magnitude of u. I'm not going to write the whole damn thing again. Magnitude of u, which for us is what? 3 times magnitude of v, which is 7 times sine of 31. Make sure you're in radian mode degree mode on your calculator. You compute that. 21 sine 31 degrees, and you get an answer, whatever it is. Anyone do it yet? 10.82. And that is the length of the cross product. 10.82. Now here's some other results of this. Do you remember with dot products, not cross, dot, that if you take two vectors and you dot them, and the answer is 0, what does that tell you about the vectors? They're perpendicular. So you take two vectors, you dot them, you get 0, they're perpendicular. Well, with the cross product theorem, it says if you take two non-zero vectors and you cross product them and you get the 0 vector, then they were parallel to begin with. Now, think about that. Let's say, again, if I cross these two vectors right here, if I cross them, is there a vector that's going to pop out of these? Yes, right? If I cross these two, is there a vector that's going to pop out? Yes? But what if they're the same vector? What if they're scalar multiples of one another? They're parallel. So they lie together on the same line. Now, if I cross them, where's it going to pop out? What's perpendicular to both? There's infinitely many vectors perpendicular to both, right? And we already saw that when you cross to the same vector with itself, we got 0, right? So what this tells us is that if your cross product, not dot product, if your cross product is 0, they had to be parallel. If they're parallel, the cross product has to be 0. So again, it's the if and only if statement, both directions. We might need that at some point. Yep. Yeah, I mean, it's just a result. This one isn't used as much as the dot product being 0 gives you perpendicular. Zero vector. The cross product spits out a vector. So that's the 0 vector. Yeah, just put that little, I think it was supposed to be bold, but then I resized things, and when I resized it, it lost the boldness of that 0. I tried to resize everything to fit on this screen when I was projecting in the room. So when I did that, some of my fonts got messed up. All right, this is a nice result. It's actually really strange, though. The area of the parallelogram formed by two vectors. So if I take two vectors, again, and I put them out in space like this, then you remember how we can create a parallelogram out of that? Well, guess what? The area of that parallelogram is equal to what? The magnitude of the vector that popped out. That's what that says. And that's beyond the scope of this class as far as showing why that's true, but we'll take it on faith. The magnitude of the cross product is equal to the area of the parallelogram formed by U and V. And my picture down here, I'll have to pause my video, I think, again. Let me just try it. Yeah, it doesn't like it. That's really a piece of junk. Oh, shit. This video is going to be all over the place. Find the volume of the parallel pipette formed by these. Let me see how much more I've got here. We're almost out of time. We have 10 minutes. Okay, I'm going to show you one thing, and then I'm going to let you finish that problem on your own in class. The idea of torque, okay, the idea of torque, you have a wrench or something, you apply a force to it. Okay, you can actually use the cross product to somehow correlate with torque. Torque is defined to be, in fact, R cross F, where R is the position vector of the rigid body, the wrench, and F is the force acting on the wrench. The direction of the torque vector is determined by the right-hand rule. Further, the magnitude of the torque is the magnitude of the cross product. So I'm going to bring up a demo here in just a second, but I'm going to draw it on the board. If I have a bolt, let's just say I have, you know, some sort of hex bolt or something like this, and I put a wrench on it. This is my wrench. Right, I put this wrench on this, and I have the handle out here. Craftsman, of course. No. So I get it, and I apply a force. Let's say I grab this thing, and I hold my arm perpendicular to this, and I rotate. And as I rotate, I keep my arm perpendicular. I'm applying a force, right? That, the torque, okay, the torque is a force that's going either in or out, depending on which way I'm turning it, right? Torque is that force. Now, if I grab this wrench, and let's say instead of holding it like this, I change my force like this, and I push this way, is my torque going to be as strong as it would if I were coming at a right angle with it? You wouldn't think so, right? Well, what if I come straight on it like this and try and push? Not, right? That's right. So look what happens. Right now, I want you to look at this. My arm coming down is like the force vector, okay? And then the vector coming out from here to here, okay, is our R vector. Got it? Then when I cross the two vectors, I create the vector going into the board or out of the board. That's my torque, right? According to what we said, if I move my arm like this, my force and my R are what? Parallel. And now the cross product of two parallel vectors is what? 0. So if I'm pushing on this, I'm getting no torque. I just look like an idiot pushing the end of a wrench into a bolt, right? How do you get the most force? How do you get the most torque? 90 degrees. Now why? Because if you go back to that formula that said the magnitude of the cross product equals magnitude R, magnitude F, sine of the angle between them, then if I want to make the magnitude of this, which is my torque, the biggest it can be, I can't control the radius. I can control the force, but the angle here, if I can make this the biggest possible it can be, then that would make my torque the biggest. What's the biggest sine can be? 1. Where? At what angle? 90 degrees. So if my angle between my radius and my force is 90, I get the greatest possible torque. Anything other than that, it dies down. So in my picture here somewhere, time for that. The homework is right here. And we finished this section, so you should be able to finish this now. 10.4 is done. How are we on our subjects here? Where are we supposed to be? Today's Wednesday? No. Yes. We finished 10.4. We're right on track. Okay? So we got 10.5 next week. And your take-home test, your first one is due when? Wednesday. And you need what we're going to do in 10.5. So there's stuff that we're covering Monday that you need to be able to finish the test that's due Wednesday. I'm going to spend the better part of this weekend figuring out all this stuff with the video. I think what's going to happen is I'm going to have to give up drawing on top of my slides. I'm just going to have to be using OneNote. Just go back to the old-fashioned right here. On the slides, I know, but I give up the 3D turning. Is that worth it? I don't know. What do you think?
I don't think you use 3D turning.
Yeah, you're right. It would probably be better if y'all reminded me every time I pause the video to unpause it, because that's going to be my problem. Yeah, it is the video. The video capture, because if I turn the assistant off, the video capture right now, I cannot go to here now, and I cannot rotate this. I can't do anything with this. All right, I'm going to try and clarify this problem here that kind of caused some trouble in class. What we're trying to do is show that we can find a v, that the component of u on v is equal to 3. So I'm going to start by defining a vector v to be v1, v2, v3. I don't know what those are, but I need it to satisfy this, which means that I need v dot u over the magnitude of v to be equal to 3. So first things first, what is v dot u? Now when we dot the 2, we get 4v1 minus v3. Now what is the magnitude of v? It is the square root of v1 squared plus v2 squared plus v3 squared. Okay, so we need, when we say over here on the right side that we need this to be true, then that's the same as saying v dot u needs to be equal to 3 magnitude of v. Now in class what I did is I said, okay, let's let the magnitude of v be 1. That causes some problems though, because once we fix it to be 1, there's certain restrictions on what the components can be. So I'm going to let it be a little more flexible here. The way I show it now is trying to avoid this in class, but I think it'll make more sense. Let's go ahead and just write out what this is, replacing our dot here and our magnitude in this equation with those two expressions. So we have 4v1 minus v3 is equal to 3 times the square root of v1 squared plus v2 squared plus v3 squared. Now we need to work through this. This is a pretty ugly looking thing here, but I'm going to try it. I'm going to square both sides of the equation. When I square the left side, that means I have to actually take the quantity and square it. So I get 16v1 squared minus 8v1v3 plus v3 squared. Now when I square the right, I get a 9, and then everything under the root, it basically appears without the root anymore. So we get this. Okay, now this is a very ugly looking equation. I'm trying to figure out what v1, v2, and v3 are to make this true. So let's notice a couple things. Remember back in the dot product when we did our v2s, no matter what v2 is, it's dead. It's going to get killed off. So I'm going to choose to let my v2 be equal to 0. So we did this in class, same thing. Let v2 equal 0. When I do that, all it does is kills off that one right there. But we still have an equation with 2 variables in it. So what I need to do now is let my v3 or my v1 be something. I'm going to choose to let my v3, be equal to, I'm just going to pick a number now. The number I'm going to pick, I could let it be 1 or 2 or 3. I can't let it be 0. Check it for yourself. If you let it be 0, then your solution for v1 becomes 0, and then they're all 0, and then it doesn't make sense. So I'm going to pick something. Now, I'm going to actually pick a multiple of basically something that's going to give me a multiple of 4, because I'm noticing that this is kind of like a quadratic equation here, and I want to be able to factor something out, so maybe it'll help. Let's see. I'm going to pick v3 to be 2. So let's see how this works out. I have 16v1 squared minus, let's see, 8. I have my 8 here, but then I'm going to multiply times v3, which is 2. So I get minus 16v1, then plus my v3 squared, which is going to be 4. And that equals 9 times my v1 squared plus, again, my v3 squared is 4. So I have 16v1 squared minus 16v1 plus 4 equals 9v1 squared plus 36. Now what I'd like to do is just move everything to one side. So I subtract a 9v1 squared. I get 7v1 squared. Let's see, I have minus 16v1. And then, let's see, I have negative 32. When I subtract 36 from both sides, equals 0. Now, those are some ugly numbers. But now I'd use a quadratic formula, okay, and I would get solutions. V equals, and I'm actually going to go ahead and get on Wolfram Alpha real quick, because my calculator doesn't have batteries, and I'm going to get a decimal solution. Okay, I'm done. As expected, I get 2 solutions. I get negative 1.2815, and then the other solution is 3.5672. I'm just going to avoid doing the exact answer because all the radicals and stuff gets kind of ugly. So that's what V1 is supposed to be. I'm going to just choose one of these, and I think I'll just go with the positive one just for the heck of it. And let me see if I can get my vector V to work out now. So the V, remember, was V1, V2, V3, we said that V1 was going to be 3.5672. V2 we said was 0, and V3 we picked to be 2. So that's coming 0 and 2 comes from right there. And then, of course, what we just got as our answer is here. So let's check some things. What is U dot V over magnitude of V? All right, U dot V. So I have to take my U and dot it with my V. Remember, U dot V was right here. It's 4 times whatever I just got, 3.5672 minus V3, which we said was 2. So again, real quick, I'll be back. Okay, I've got 12.2688. So that I'm going to come back down here and put it on the bottom here. I get 12.2688 divided by the magnitude of V. So magnitude of V, I'll do that down here. The magnitude of V, remember, is the square root of all the components squared. So 3.5672 squared plus 0 squared plus 2 squared is 4. And again, I go get it. All right. Now I've got, let me get this out of here. I get 4.08961 or something like that. And that's going to be on the bottom, 4.08961. Now if I divide those, and I'll keep you standing by here while I do this, 12.2688 divided by that, I get 2.99999, so approximately 3. And remember, that's what we wanted, right? We wanted way up here, there, for that to be true. And we just actually showed that that's true. So this vector V is a choice. It's not the only one. There's actually an infinite number of them, but that is a choice that would satisfy that the component of U onto V is equal to 3. So apologize about the confusion in class. I was trying to avoid having to do all of this, but looks like that's what we got to do. Okay, hope that helps.